Hello, I am Shubhadeep. Today I want to provide a thesis synopsis for my PhD work. I did this with Professor Navakanta Bhat at the Center for NanoScience and Engineering at Indian Institute of Science at Bangalore. And my presentation is titled Materials, Processes and Device Design for High Performance Sub-thermionic MoS2 FETs. The shrinking of the field effect transistors, commonly termed as CMOS scaling, has revolutionized the semiconductor industry and impacted most aspects of human life. However, this decade-long successful trend of scaling the FET is now facing serious fundamental and technological challenges, resulting in diminishing economic returns. Clearly, the road ahead needs breakthroughs in new materials and device design. The advent of 2D materials, especially semiconducting transition metal dichalcogenides, offer a unique opportunity. However, translation of this promise into realizable technology and products is still an open challenge with several core issues to be addressed. The primary motivation of this thesis is to address the fundamental problems in the realization of high performance FETs on 2D semiconductors, especially in this thesis disulphide or MoS2. The focus areas can be summed up briefly as contact engineering, area selective doping, dielectric engineering, and steep subthreshold slope architecture. This brings us to the first part, which is contact engineering in MoS2. Variability and difficulty in achieving good ohmic contacts are major bottlenecks towards realization of good MoS2 based devices. The role of surface states engineering through a simple sulfur based technique is explored to enable reliable and superior contacts with high work function metals. Sulfur treated multi-layered MoS2 FETs exhibit significant improvements in ohmic nature, nearly complete elevation in contact variability, 2 times gain in extracted field effect mobility, and 6 times drop in contact resistance. Raman and XPS measurements confirm the lack of additional channel doping and structural changes after sulfur treatment. From temperature-dependent measurements, the reduction of Schottky barrier height at nickel MoS2 and palladium MoS2 interface is estimated to be 81 and 135 millielectron volts. This first report of surface states engineering in MoS2 demonstrates the ability to create excellent contacts with high work function metals without additional channel doping. Moving on to the next section, which is doping through vacancy engineering. The lack of techniques for counter doping in 2D semiconductors has hindered the development of PN junctions, which are basic building blocks of electronic devices. Low energy argon ions are used to create sulfur vacancies and are subsequently filled with oxygen to create p-doped MoS2. This incorporation of oxygen into the MoS2 lattice and hence the change in band structure reveals the nature of the p-type doping. These changes are validated by a combination of material characterization techniques and density functional theory calculations. Electrical measurements reveal a complete flip in carrier polarity from N-type to P-type. Employing top-gated transistors and area-selective vacancy engineering only in the contact regions facilitates the enhancement of P-type transistor characteristics. Finally, an in-plane type 1 straddling heterojunction with rectifying contacts and excellent broadband photoresponse is demonstrated and explained using band diagrams. The spatial abruptness of less than 100 nanometers of heterojunctions is ascertained using Raman mapping. This process of vacancy engineering, which enables air-stable, area-selective, controlled CMOS-compatible doping of 2D semiconductors, is envisioned to open new vistas in the development of high-performance electronic and optoelectronic devices. The next section deals with scattering in dielectrics. The ultra-thin channel in 2D semiconductors, although plays host to several interesting properties, also results in strong interactions known as scattering with the surrounding medium. The overarching dominance of surface optical phonons in 2D charge transport and electric engineering ideal nitride-based dielectric environments for large performance gains is demonstrated. By employing semi-classical models, charge transport in MoS2 transistors fabricated on 3 conventional substrates, silicon dioxide, aluminum oxide, and hafnium oxide, is contrasted with a newly introduced CMOS-compatible nitride-based dielectric aluminum nitride. Unlike previous reports, which focused only on charge impurity scattering, this work presents a new paradigm utilizing high optical phonon energies intrinsic to stiff nitride bonds. This results in substantially lower surface optical phonon scattering in an MoS2 FETs, which directly influences the mobility of charge carriers in the transistors. Finally, leveraging on these insights, high performance sulfur passivated MoS2 FETs with an optimum all nitride dielectric environment having field effect mobilities of 72.8 centimeters square per volt second is demonstrated. This work is envisioned to address important issues in design of dielectric environments for a host of applications based on 2D materials. The next section describes high K dielectrics for top-gated MoS2 FETs. A new substrate 30 nanometer hafnia on silicon is developed for high-performance backgated molybdenum transistors. Record drain currents and transconductance have been achieved for 1 micrometer channel length multi-layer MoS2 transistors. The intrinsic mobility extracted from Y-function technique is 3 times more than the silicon dioxide substrate. The drastic improvement in transistor performance is attributed to a combination of 3 factors. First, efficient gate coupling with EOT of 6.2 nanometers. Second, charge impurity screening due to high K dielectric. And third, very low contact resistance through sulfur treatment. Next, we break the paradigm of atomic layer deposition and employ functionalization-free E-beam evaporated top-gated high K HFO2 to achieve near perfect subthreshold swing operation. The E-beam evaporated 30 nanometer HFO2 gate dielectric has optimized processing conditions, yields very low EOT and very low interface traps density. The top-gated MoS2 FETs demonstrate field effect of 63 centimeters square per volt second. This FET employed along with the depletion mode N-channel load to demonstrate inverter circuits with a gain factor of 9. Finally, we move towards our promise of an ideal transistor. The inability to scale supply voltage and hence reduce power consumption remains a serious challenge in modern nanotransistors. This arises primarily because subthreshold swing of the thermionic transistor, a measure of switching efficiency, is restricted by the Boltzmann limit to less than 60 millivolt per decade at 300 Kelvin. In a completely different approach, by introducing concurrent tuning of thermionic and tunneling components through metal semiconductor Schottky junctions, we attempt a rendition of an ideal low-power transistor. This is achieved by combining the advantages of tunnel FET with steep subthreshold slope with that of a thermionic FET which have very high on currents. And all of this is done in the same device. Dual-gated MoS2 FETs are fabricated with careful deliberation of device architecture and materials processing. This device is capable of operating in 2 distinct regimes. First, a low-power tunneling regime with steep subthreshold slope and operational voltages of less than 0.5 volt, or a high mobility, high on-current thermionic regime. Next, an intuitive modification in the device structure can dynamically tune the transmode from off to on state, thus combining the dual benefits of tunneling and thermionic transport in the same operational cycle. These devices demonstrate hysteresis-free steep subthreshold swing with minimum subthreshold swing of 3.4 and average of 29.3 millivolt per decade and high mobility of 100 centimeters square per volt second. All of this is achieved at an ultra-scale drain voltage of 10 millivolts. A detailed mechanism involving the independent control of Schottky barrier height and width, efficient device architecture explains the functioning of these devices. The performance of the reported transistors is much better than the state-of-the-art TFETs and therefore promising candidate to supplant them. We envision the reported thermionic tunnel FETs to create new avenues for the development of next generation high performance green nanotransistors. To conclude an interesting journey, the first MoS2 FETs fabricated by us demonstrated a mobility of 100 centimeters square per volt second and subthreshold slope in the excess of 2000 millivolt per decade, and through systematic scientific analysis and engineering optimizations, we transform these metrics into the best reported values in literature of 100 centimeters square per volt second and 29 millivolt per decade for 3 decades respectively. I thank you for your attention.